Okay, let's begin. So we don't have many students come here. So if you don't have your group member, then you can join to your join with other student next to you, even though you're not in the same group. Just sit together. I'll give you the chance to get your name tag if you want, but sit together because we're gonna have some group activity. Okay, so today we're going to have a line integral. So we talked about the curve. So when the curve is defined to be a the image of continuous path, continuous function from an interval from to the n-dimensional space. So given that such curve, we want to integrate wait. So I think there's another typo, sorry. So this is ... So we need to integrate that some function over that line. Okay. So it's the same thing. Oh, sorry, what happened here? Oh, sorry. So I forgot to put this one. Okay, yeah. So we want to integrate over a curve. So it's the same thing as we integrate over an interval. For when you take a integration of single variable function, you integrate over an interval. So you can think of interval as some sort of a curve on the straight line, but when you think of straight line is inside of the xy plane or xyz space, this is the curve. So when you take the integration of single variable function, you're actually taking a line integration. So we not only want to take the line integration over the line, we want to take the integration over the curve, which can be non-straight line. Okay, so what are we doing here? We are doing the same thing as we've done so far. Our domain is the curve, so our domain of integration is the curve. So when you take the integration, the idea is you split the domain into small pieces and you take the length, area, or volume depending on the dimension of your space domain, and then take that, multiply with the value of function you picked from that small partition, and then sum them up, right? So this is the definition. When you integrate over the curve of the function defined on that curve, you're subdividing the curve into n pieces, and you take the length of these pieces. Actually, this is not exact length of the part of curve, but actually the length of the line approximating that part of a curve. And then you multiply with the value of function you picked in between these two endpoints. So, and then sum them up. So when you send this number of subinterval to infinity, you can make this approximation, the lines that are approximating the curve almost equals with the line, and that will give you the line integration. Okay, so well, let's first wait. I think I had a picture here. Yeah, there is a picture. Yes, I'll explain the picture later. So let's actually follow the definition here, and let's try to find the calculation done, and then we'll do it. We'll look up the meaning of what the line integral is. So think about a line, the actual line, joining from 0, 0 to 1, 2. So that's your curve. I want to integrate a function, this function, 2x plus y, over this line. Okay, so what I'm doing is I'm taking the partition here. Well, let's see, this is straight line, so I can take equidistant partition. So I can, so how long is this line? Square root of 5. So let's see, I want to first parameterize this line segment from interval 0, 1 to C. Let's see, if I want the curve start from 0, 0 and end at 1, 2 with the parameter t run from 0 to 1, I can make it into t, 2t, right? So that's my parameterization. And let's see, I want to subdivide my domain of interval from 0 to 1 into n partition. So ti will be I over n. So so cti will be I over n, 2i over n. And if I take, so this is, I denote it as ci. So if I want ci minus 1, ci vector, I don't care about the vector, but the vector is simple anyway. But I actually care about the length, right? So you can compute the length by plugging these coordinates, but it's easy because it's simply n divided by total length of this line segment, which is square root of 5. So I know this, and let's follow the definition. So I want to integrate over 1 to n, so entire n segment, and I want to take some number in between ti minus 1 to ti. So I can take any of this. So same idea in the Riemann sum of the definite integral. But let's put it like this for now. And then I want to multiply with the length of the line segment. Okay, well, how about we put ti star to be simply ti? Okay, well that might be actually make it simpler to compute. So n goes to infinity of k1 n, and since I know that this is function, so function is, so what is x? So this is my x and this is my y coordinate at ci, right? So I plug in that value, so 2 times I over n plus y, 2i over n. So that's my function value measured at ci, okay? And then multiply with the square root of 5 over n. Okay, so this whole thing becomes 4i over n. And let's combine all these constants. So we have 4 square root of 5, the limit and summation. And what we have inside, we have n square denominator, and on the numerator we have only I, right? We only have I. So we have 4 square root of 5 times n, so I shouldn't forget the limit yet. So limit and n square, and when you sum over 1 from n, then it's 1 over 2 n plus 1. So it's 2 square root of 5. So that's your line integral. So whenever you say line integral, it's a number, okay? So we're not talking about the meaning yet. We're talking about line integral as a number that you obtain by taking the Riemann sum and taking the limit. Okay, here's a more practical way of computing the line integral. So most of times when you have a curve, it will be given as a parametric curve whose parametric function is differentiable, because you want a smooth curve, not weird curve. Maybe it could have a finitely many sharp corners, but not weird curve that like almost impossible to draw. So when you have such nice parameterization, your line integral can be actually computed in a definite integral over the single variable function. So what's the integrand here? So first you have function value given from the line integral here, and you multiply that function value with the speed of your parameterization. So you can see what it now means. So what it actually does is what happens when you multiply the speed with the dt, which is the small increment of time. So t is now considered as time. When you multiply the speed with time, the amount of time, then it's the amount of distance that traveled along the curve. So you're actually multiplying the function value with the distance that traveled along the curve. So it's not just the distance. Your distance are multiplied with the function value. That's what you're taking the integration for. And if you have, in some sense, non-differentiable curve, which means that you have certain points that is not differentiable because of a sharp corner or breaks, then you can split your line curves into several pieces, finitely many pieces, that you can parameterize by differentiable function independently, and then sum them up to get the entire line integration. Okay, so remember this formula, because this is important. This formula is, in practice, what you have to apply almost all the time. So I just gave you, by definition, I just gave you the example that you can compute the line integral by definition, but it's, you know, as if it's you apply all the time Riemann integral. It's too much, too complicated. Although it's a definition, it's too complicated. So this is more practical way of computing the line integral. So let's think about the meaning first and then look at the example. So what's the meaning here? So as I said, I just gave you the meaning by the formula, but let's think about it in geometric sense. So suppose that we have a function whose value is always positive, and we want to compute the line integral over the curve. So as I said, let's say if curve is lying in xy plane, you can think this as a curve inside of xyz space. So the curve lies in xy plane in the flat space. You can think of this value function as the height that's sticking from the xy plane to the z direction, positive z direction. So when you draw this line with the height of function value, and let's see, you want to move along the curve and your height is changing, the length of line sticking from xy plane is changing, so that it makes some sort of a curved wall. Okay, so it has an area. So the line integral is actually the area of that wall. It is the area of that wall, because you can flatten out this wall. Let's say if you want to, if this is the fabric, you can iron this into a flat surface and then make it into actually flat without loss of any area. So when you take this into a flat surface, making this curve into a flat straight line, then what you see under the curve boundary on top is the area that you get from the line integral. That's the meaning of the line integral. Well, that's only when you have a positive value of function. Well, if it's the same thing as the meaning of the integral. Well, when you have a negative value, then it goes below the xy plane, and it kind of means the a negative area. So you can think of this line integral as geometric something that geometric meaning that has a geometric meaning. So let's think about other example. I think I have more examples. So we'll do this first and together, and then I'll let you do the next one. So now we have a practical way of computing the line integral. if you have a differentiable function as a parameterization of curve, so, and you have a meaning of the line integral, let's think about this one. C is the boundary of unit circle centered at 0. So this is the curve C in xy plane. But I'm actually looking this curve as in the xyz space. I want to find the line integral. So that means I want to see how the area of the wall bounded by the graph of this x squared times y squared, but I only want to take the area that is on this curve. So I want to parameterize this curve first, since it's the unit circle area, curve, so I can parameterize by cosine, sine. And let's plug that in here with a formula. So here, our formula is a formula of definite integral of single variable function. So what's the interval of domain? It's from A to B, where A to B is coming from the parameterization of our curve. Since my parameterization has the domain from 0 to 2 pi, in order to make a full circle, I need to take the integration from 0 to 2 pi. And even though I have a function x and y, when I take the parameterization, I need to take the substitution of x and y in terms of that parameterization. So this is my x and this is my y. So I need to take cosine square and sine square, and that's not it. Don't forget the length, the speed of this parameterization. But this is simple. Well, but let me put it first, just to remind you that you shouldn't forget this. So what is the C prime? So C prime is the speed, not the speed, it's a velocity. So it's a minus, it's a vector. So I'm going to use the vector notation here. Here, minus sine t, cosine t. But this is actually the unit speed, always. If you take the norm of this vector, it's always 1, and it actually goes around this unit circle in a unit speed in this direction. It only changes the direction. So I know that it's always, this is always 1. So I can get rid of this as 1. So what I'm actually taking is the integration of this. So let's see, this is 2 sine 2t square divided by 4. So I intentionally put the 4 and take out the 4 so that it makes, no, sorry. What I'm trying to do is cosine t, sine t first, and square dt. So I can take it as sine square 2t dt, and then using the formula of sine and cosine square, it's 1 minus cosine 4t over 2 dt. So well, cosine part cancels out to 0, so only have 1 over 2, so it's pi over 4. Okay. So you can imagine that this picture, the line integral, is representing an area under this graph z equals to x squared plus x squared times y squared, and we only want to take the section lies on the curve. So we will see it's not a cylinder because it has a different height along this. Well, maybe, is it a cylinder? No, it's not a cylinder, right? So it has a different height for each point on the curve, but it's kind of, I think, symmetric. But anyway, so it's not easy. You can't just calculate the area by taking the length of the curve and then take the height. You have to integrate over the line. All right, so let's try to do this one. Well, maybe it's a little bit challenging, but I think you get the idea. If you get the ideas right, you will see the same thing going on. So what is the line integration over the three-dimensional curve? So same thing, you want to integrate, you want to take the line segment and then multiply with a function. Now, it's not easy to interpret this line integration as some sort of a geometric object, because if you want, then we need a 4-dimensional space, because you have a line already sits inside 3 dimension. It goes along 3 dimension. Then what's the height? Well, maybe it's the 4th dimension that you want to measure the height, but that's hard to imagine. So, well, if you want to, like, if you insist to interpret this line integration as a geometric something, then you can do so. It's an area that sits inside 4 dimension, but well, it's hard to visualize. So, but anyway, you can compute the line integration in the same way we do before, because the formula here is the same. It doesn't say anything about the 2-dimensional, 3-dimension. It's always in the n dimension. So you have a value function measured at a certain point on the line, and also, if you want to, you can find out the speed of the parameterization and multiply it with the function value and integrate. That's all we need. So it doesn't have to be a 2-dimensional curve. It can be applied to a 3-dimensional curve. It actually works for any n-dimensional curve, but when you have a 4-dimensional curve, it's hard to imagine what it looked like, so we don't talk about this here. So let's try do this example. And as I said, if you don't have your group member came today, then you can sit next to any friends next to you. So I'll let you take your name tag if you don't know your names of your friends. And let's start with this example. 종이도 가져가세요. Is there any questions? Okay, some got right and some are still thinking, but let's do it together. And since we have another example in the next slide, so we can do it together. All right, so one thing about when you see the line integral is that it's a symbol, it's a notation, okay? So when you compute something, so it's a philosophical. It actually goes to the philosophical conception of the mathematics. So when you see some formula, some people think it as a certain symbolic rule. Let's say if you have a plus sign, a minus sign, you remember the rule of adding or subtracting, and you try to do it like a machine, like as if you're have an algorithm to carry out these symbolic expressions, and you do the computations. But what actually the symbol means is it's meaning, or it's statement that we decided to abbreviate into these kind of symbols. So this line integral is actually what it says is I take this entire function as three variable function which has a real value, and I want to take the curve. So this curve is something like, is it one? No, actually it has to goes one round, right? So it has to go one round here. So it's a spiral line, what is it? Spring or something like a spring on the three-dimensional space. So it goes up when it rounds up once around the origin. And I want to integrate over this curve of this function, which means that I want to take the small pieces of this curve and then multiply with value of function and then add them up together. So as I said, it's not easy to identify it as a geometric thing, but if you think about the meaning as a mass of a thing, then you can imagine that this line integral gives you the total mass of this one-dimensional curve inside of three-dimensional space, where the density of this mass is given by this three-variable function f. So imagine that you have a entire space filled with something, or maybe air or whatever, or actual mass, but the density of this mass is given by x squared plus y squared plus z squared. So which means that if you're at the center origin, then it has no density, but when you go out from the origin, it has more and more density depending on the coordinate. So and then imagine that you scoop out this curve along the parametric curve right here, and you want to take them out, or you just get rid of all the rest of the parts that except for the scooping part. Then you want to measure the mass of this object. That's your line integral. So let's try so that's the meaning, and the formula or definition of this symbol, it actually depends on that meaning, but you can forget about the meaning and start to just compute by the definition of the formula. So since I have interval from 0 to 2 pi, so this line integral becomes the single variable definite integral from 0 to 2 pi of the function, this function, f, whose x, y, z is replaced by the parametric function in terms of these three. And then, it's not it, I need to multiply with the speed of the movement because I want the length. So this whole thing is replacing ds part. So ds, I see some people are asking what the meaning of ds. It's the infinitesimal increment of the line segment, or infinitesimal movement of, or distance that moved from one point to another along the line. So if you want to find the infinitesimal distance, you need to multiply the speed times the infinitesimal amount of time it passed. So it's 0 to 2 pi of cosine square sine square plus t square. And then now you have to take the differential of your parameterization. So c prime t is minus sine t cosine t and 1. Okay, so when you take the norm, it's square root of 2. Okay, so this whole thing becomes 1. So basically you're integrating 1 plus t squared over 0 to 2 pi. And that's not hard at all. So you get an answer here. Okay. So again, I want to emphasize that when you see this line integral, don't attempt to carry out your computation symbolically. Okay, try to think about meaning, and also try to recall the formula that gives the answer to that, that gives the same value to what the line integral is meant for. So let's try to think about this one first, and the next. So although I mentioned that the line integral symbol, like this one, f ds, is symbolic, but sometimes it's necessary to think about purely and symbolically to make the calculation simple. So here I have a curve as a pieces of line joined together. So one piece is 0p, this one, let's call it 1, and this is 2. And well, let me be more technical here. So C1 and C2 and C3. So as I said, of course you cannot parameterize this entire three pieces of curve into one formula, because they're all in different shape. And there are 2 points, P and Q, which is not differentiable because there is a sharp corner. So you have to separate your line integral. So this line integral becomes, so let me abbreviate this into F, line integral over C1, line integral over C2, and line integral over C3. So as you can see here, I dropped the ds here because, as I said, symbolically, ds has no meaning. It only gives you that, indicate that this is the line integral. But as you can see from the notation of integral symbol over this curve symbol, you can see that it's a line integral, obviously, because this is not a definite integral, any similar to definite integral. So anyway, I want to integrate these 3 line integral independently and then sum them up. Think about the line integral over C1. I'm moving along x-axis, right? So the actual x-axis. I'm not changing along y-axis or z-axis. Only I'm my increment of the line segment or the distance is along the x-axis. So in this case, in the C1, let me erase this one, C2, C1. My increment is actually only along the x-axis. So I can just replace my ds into dx. So I'm now I'm actually moving back and forth to the symbolic notation and then non-symbolic notation here. But what's good about sometimes putting into a symbol that has the meaning, a concrete meaning, is that you can think this symbol as if it has a real meaning. So ds, as I said, has no meaning, but here, if you think this line segment, the length of a small line segment, this line segment is always parallel to x-axis, so you can identify the length of line segment as if it's the same as the increment in x coordinate. So I can just think this as this ds as dx. So when I say dx, now I'm talking about the definite integral. So what's my domain? X is changing from 0 to 1, right? 0 to 1. But don't forget that this f is not single variable function, but I'm going to consider as if it's a single variable function because y, z coordinate is not changed. So when I'm moving along C1, y is 0 and z is also 0. So I can think that this function fx plus y plus z is single variable function in terms of x, considering y, z are constant to 0. So this is same as 0, 1 x dx. So it's 1 over 2. Okay? So I'm telling you that, so first I told you that you shouldn't think about this line integral symbol as something that has the meaning, but here, sometimes the situation is right. You can think of this as a symbol that has a meaning and make this calculation simple. So C1 integration is this one, and how about C2? And how about C3? It's a similar thing, so I'll give you the hint and then let you do the rest of the calculation. So on the C2 side, what's the axis that is changing? It's only changing the y coordinate, right? So x and z coordinate is not changed. So your line segment, ds, the line increment, ds, is same as dy. So you can integrate over dy by fixing x and z coordinate. And then on the C3 side, you can think about which part, C2 is changing z coordinate, C2 is z coordinate because it's a vertical up. And C3 is now changing the y coordinate, right? Oh, by the way, this is x-axis and this is y-axis and this is z-axis. That's a standard picture that you generate when you use the Python. So anyway, try to compute the line integral on C2 and C3 and then get the entire line integral. Try yourself. Use the rest of the parts. Okay, I'll give you the formula and then we'll do the rest of the calculation as on homework. So how about when you move along C2? So along the C2, x is 1 and z is changing, but y is also 0. So we don't want to change the value of function. Function has formula x plus y plus z. We're not changing the function. So it's not the change that I made f into x. I simply plugged y equals to z equals to 0 into the formula to get x as a final formula of function. I'm not changing the value of function. I simply look at the value of function. It turns out to be the same as x. So when I look at the value of function along the C2, my value only depends on z, but y is 1 and z, x is 1 and y is 0. So we have integration 1 plus z in this case. Okay? So this is my value of function because x is 1, y is 0. So when along the C3, now x and z is also 1. So the value of function is 1 plus y plus 1, right? So we have 2 plus y dy. Okay? So the integration domain is 0 to 1 all the time because we are moving along 0 from 1. So this is how you compute each line integrals and you combine all of them to get the entire line integration. So this technique is only possible if you have a line that moving in a straight line along x or y or z axis. Okay, so I'm telling you that I'm trying to giving you the meaning of what this ds part is. But in general, you cannot just replace ds into one of dx, dy, dz. Okay, so the line integral on the function is just the one step for defining the line integral on the vector field. So let's talk about the vector field. So in the engineering mathematics 1 in the previous semester, you probably remember about the vector field. It appears in one part. I will define first. So vector field is a map from n-dimensional point to n-dimensional vector. So in general, you want to map the same dimensional point to same dimensional vector. So that's how, or the way the vector field is defined. So this on the picture on the right is generally how you visualize the vector field. So every point that arrow starts is the point that is on the domain, and the arrow, the size and direction represents the vector that is assigned to that point. So you can think of the vector field as if it's a flow of water on the surface in this two-dimensional case, or it's a wind that blows on the surface of Earth and so on. So let's talk about some operation that we can put on to the vector field because it's going to be used in the next part when you discuss the Green theorem, Stokes theorems, and divergence theorem, and also some other stuff about the potential function. So if you have a partial differential operator, del del x to del del z, you take that as a component of a symbolic vector called a nabla. So I'll give you the name of this. So nabla, or sometimes call it gradient. So, but the name of the symbol is nabla. So I will just call it nabla here. And you can take the cross product, some sort of a cross product between the nabla operator and the vector field. So let's suppose that the component of vector field is PQR. So each PQR are real valued functions. Okay, so there are real valued function with the 3 variables. So P is function in terms of x, y, z, and Q is also same, and Z is also same. So therefore, you can take the partial differential on any part operator on the nabla, and you can define this operation. Well, what's the component? I mean, what it is it's a 3-dimensional vector. It's actually a vector field because all the components are a 3-dimensional function. So these are 3-dimensional functions, but not the same function defining the vector field. So it is three-dimensional vector field. Okay, so nabla cross F is three-dimensional vector field called curl. Okay, so it's called curl of the vector field. And we'll talk about the meaning of the curl like maybe next time. But here, let's focus on how we compute the curl. So it's computed by taking some linear combination of partial differentials of each component. And you can see from this formula that it is actually the same as taking the cross product of two vectors, nabla and the vectors. So if you think of this as a cross product of these two vectors, put the components of these two vectors into the second and third row like this one, and then just perform the cross product as if they are actual vectors. Although the operator is not a vector, which has a real value component, but just consider it as if it's a real number. So what is the, and then take the determinant because you're taking the cross product. So what is the component, what is the sum end when you take the determinant that has E1 part applied, multiplied? So this is equals to, so first let's see, adding all this multiple of this direction, and this is addition. So remember how we defined or compute the determinant of 3 by 3 matrix. So this is plus and this is minus. This is minus. So think about the plus part. So among the plus part, think about this part. So this one is E1 times del del y times R. And also think about the minus part, this one, okay? So and then minus E1 del del Z G, Q, sorry, so Q, right? So as I said, when we take this as if it's just two three-dimensional vectors, but once you write this out like this one, now think about the meaning of differential operator. You're not actually multiplying the differential operator with the function. You're actually apply or acting this operator onto the function. So you're actually taking the partial differentials on y, r in terms of y, and same for q in terms of z. So therefore, the E1 vector, now don't forget the meaning of E1. E1 is 1, 0, 0. So this is equals to 1, 0, 0 multiplied to ry minus qz. So these component goes to the first x coordinate of the z of the three-dimensional vector representing this curl. Okay? So that's the same thing as here, this one right here. And rest of the parts are similar. And let's think about the divergence. So divergence is the same. So you get the, sometimes I put it not the dot, but using the inner product symbol, but it doesn't matter, is done by taking the nabla as if it's a three-dimensional vector and inner product with the vector f. So the first operator, del del x, applies to p, and the second for q and third for r. So that you get the sum of these partial differentials. So what is this? This is not a vector. This is three-dimensional function. Okay, that's not three-dimensional. Three-variable function. Okay, so the nature of curl and divergence are different. Curl is three-dimensional vector. Divergence is three-variable function. Okay, and you can also define in the divergence case, divergence of two-dimensional vector field simply by taking the linear product of two-dimensional vectors. But be careful that we don't have a notion of curl for two-dimensional vector field, but there is a notion similar to that, but we'll talk about it next time. But anyway, that's the rule that you can, that's the operator you can put on the vector field. And here is another operator. So it's not the operator you can act on the vector field, but it's a way you can generate a vector field. Let's say we have 3-variable function. You want to apply the same nabla onto this 3-variable function, not the vector field. It's f, small f, not boldface. It's a 3-variable function. When you do that, you just take this nabla as if it's just a 3-variable function, 3-dimensional vector, and then as if taking this f as if it's just a constant, like a scalar, when you take the scalar multiplication on the vectors. So you apply this f on every component of nabla to get these components, the partial differentials of f. So the gradient, this is called the gradient vector field, coming from the 3-variable function. So the nature of the gradient vector field is a vector field, as the name indicates. And here are the rules. Well, it's lots of rules, but not hard. Sometimes, some of them is a bit hard, but the thing is, you don't need to remember anything, well, because you can look up anytime if you need to. You need to understand which and which doesn't make sense. So these all make sense, but sometimes when you try to mix up the nabla operator with the functions or vector field, you don't want to write down something that doesn't make sense. So let's look one by one. So here, on the first line, what you're doing is you first take the gradient vector field. So that's a 3-dimensional vector field, okay? And you take the curl. That's possible because you can take the curl on the 3-dimensional vector field, right? So then what it says is that you get 0 vector field, which means that the vector field maps assign 0 vectors to every point on 3-dimensional space. And look at this one. You're taking a curl of a vector field, so you get the 3-dimensional vector field again, and you take the divergence. So what's that? When you take the divergence of a vector field, you get 3-variable function. And the second equality says, after you've done this, what you get is 0 function that has 0 value at every point in 3-dimensional space. Okay? So, so what is this allowed? So having a 3-variable function and then taking a curl. Well, it doesn't make sense, right? You cannot do this. That doesn't make sense. You're not going to see this kind of equality, but as I said, be careful not to do this. And the rest of this part is similar. Well, okay, the third part is that when you take 2 vector fields and you add them together, now you can add 2 vector fields because the value of function is vectors. Vectors can be added. So that's allowed to add 2 vector fields. But in general, if you have a function that maps one point to another point in n-dimensional or m-dimensional space, then you cannot add points, right? So it's not allowed unless your value of function is a real value. But here, you can add them together. Well, the divergence of this is separated into the sum of divergence, and same thing for the curl. The curl of the sum of vector field is the sum of 2 curl. And now the rest of the part is a little bit complicated. Well, let's see. So just just try to make sense why this makes sense. So what you're doing here is you're taking a vector field and multiply with a function. Oh, what is this? It makes sense because your vector field, let's say I want to write the vector field as this because it's hard to distinguish the boldface when I write it. So this is our vector field. When I multiply f, the function, I'm just multiplying f on the vector PQR. So it's same as P, FP, FQ, FR, just having different components. So F and PQR are all 3-dimensional real valued function. You can multiply those real value of these functions. So it simply means that f F vector field is the vector field has these Fp, Fq, Fr components. So when you take the gradient on that vector field, you can rewrite that vector field into sum of two vector fields. So first sum is that, sorry, that's not vector field. It's a function, right? So when you take the divergence, it's a function. You can write it as a sum of two three-variable function with the real value. So first sum is the multiple of the function and divergence of the vector field. And the second sum is the inner product of vector field with the gradient vector field. Well, that makes sense because these two summands are both functions, not the vectors. So you can add them together. As I said, this function is in real valued function, so you can add them together. And same thing for 6, 7, 8. So 6 means that you can do similar thing with the curl. That means your output is the vector field, and it says your vector field is the sum of two other vector fields given this way, and the rest of the parts is similar. Well, that's complicated, but not that complicated. You can just simply plug in the general situation like this one into any of these formula, and then just carry out all the detailed computation, and you can see by component wise these are the same. So just tedious calculation, but not hard. And we're not going to use this much really, but maybe in the Stokes theorem, but maybe also in the complicated situation, but not really much in later lecture. So what we want to do, since we talked about the vector field, what we want to do really is to define the line integral on the vector field. So that's the key part here. So same thing, similar situation as before. I want to integrate over the curve, but this time not function. I want to integrate the vector field. So I'll give you the definition first and then try to find the meaning of this. The definition is, so this is symbol. This is just, oh, sorry. So this is just a symbolic notation indicate my line integral, okay? So it doesn't have any meaning, but I need to specify all the necessary information. That's why I put this symbol. Is defined to be, so this is symbol, this integration. So what is this? It's simply a definite integral on single variable function in terms of t. So first I have a vector field computed at the point ct parameterized by t, and then what I do is take an inner product with the vectors given by the vector field and the velocity vector parameterizing the curve. Okay? So when I take the inner product of two vectors, I get the scalar, the real value. So it's the real valued function in terms of t, so single variable function. So I'm taking integration of that single variable function over the interval from a to b. So I'll give you the example and then look at the meaning. I want to find the line integral of a vector field minus y comma x, two-dimensional vector field, along the two-dimensional curve parameterizing the circle, so cosine and sine. So let's just plug in into the formula. And so here I have FCT, so this is a vector field indicated by arrow sign above. And I take the inner product of that with C prime t dt. Okay, that's a definition according to some information here. And let's plug in the formula. So f is minus y comma x, and x and y are parameterized by cosine and sine. So instead of minus y and x, I plug sine, minus sine, and cosine t, and then inner product with c prime, minus sine, cosine, and dt. Okay? So this is same as 1 dt. So I get 2 pi. Again, the line integral of a vector field is number. Okay, so you're not gonna get the formula, you get a number. So every integration is about getting a number. So there are two things I want to emphasize here. First, the line integral over a function indicates area or mass, whatever, but it shouldn't depend on parameterization, even when you parameterize in a reversed order, reversed orientation. So it doesn't matter when you go from A to B or B to A when you take the line integration over a function. But when you take the line integration over a vector field, the orientation matters. If you integrate over A to B, that's inverse to the negative of the line integration from B to A. Why? Let's take the example here. So instead of cosine t and sine t, well, I want to go inverse. That means I want to take cosine minus t and sine minus t to go inverse clockwise orientation. So because the original cosine sine gives you counterclockwise orientation of your parameterization. When I take the minus, it's cosine t minus sine t, right? So let's try to use this parameterization instead of the first one to compute the line integral. So when I plug that in, this is now x and this is y. My vector field is become now sine t. It's now instead of minus sine t because it's minus y. Y is minus sine, but minus 2 minus cancel to plus, and x is cosine t. And what is c prime? So it's minus sine t minus cosine t. So it's same as minus sine squared t minus cosine squared t, which is integration of minus 1 from 0 to 2 pi. So you get minus 2 pi instead of 2 pi. So you get a negative value. And, well, what's the meaning of this line integral? Well, actually, it's related to the fact that you get a negative when you change the orientation of a line integral. So think about the meaning. So the line integral is the work done by the vector field along the line through the parameterization. So what do I mean by through the parameterization? So it actually depends on the orientation of the parameterization. So if you want to move the particle or any object that has some kind of a mass from one point to another along the curve C, you need to have work done, right? Like you want to lift the object from the ground to some height, or if you want to move some parcel along the surface which has a friction from one point to another, you have to apply the work. So the amount of work that you have to apply to get the thing moved from one direction to another along some certain path is the line integration. So who done the work? So, well, we simply assume that it is the vector field which has done the work. Okay, so how does the vector field is generated? Maybe it's the wind, maybe it's the human power, doesn't matter. As long as there is a vector field, we consider that the vector field has done the work to move the object along the path. So think about the orientation next. So if I move the object from the ground to the level of height, then I do the work. But what's the inverse? If I let the particle to fall down to the ground without doing anything on my behalf, then it's the gravitation that has done the work, right? So in sense, when I lift them up against the gravitation, actually giving the energy to the particle to be able to fall down, which turns the height energy or potential energy into some into what is it called? The energy about the movement, sorry, so I just forgot the name of it. But anyway, to change the energy in another form, and so on. So, but in any case, so when the gravitation has done the work, you can consider it as a positive work. Or if I done the work against the gravity, then you can consider it gravitation has done the negative work, that it turns this work into an energy that stores into the potential energy of the particle. So everything can be just interpreted as in terms of work done by a vector field. It only matters a positive sign or negative sign, where the energy go. But it doesn't matter, so just think about this as work done by the vector field. So do I have another? Oh, okay, so we don't have examples. So let's do this example to maybe, let's see. Well, we can do this together. Okay, we have more examples. So we can do this together, and then I'll let you do another example with your group. So let's find the work done by this vector field along the curve. Well, what's this curve? It looks like a circle, but you have to think about the orientation and the starting and the end points along this parameterized curve. So when you try to get the line integral of a particle or of a vector field, at least you need to have an orientation. Actually, you need to have two things. You need to have a path and orientation. So if you have given with the parameterization, that solves these two problems at once. Okay, so let's plug that in here. So all things that I want is just getting the line integration done. I want to take the vector at each point in CT and take the inner product with the velocity C prime t, and that is same as, okay, so this is x and this is y. So it's kind of complicated, but it should cancel out at some point. So minus 2 sine t and 2 cosine t square, and okay, so comma minus 2 sine t times 2 cosine t, that's y, right? And that's vector field. And inner product with minus 2 cosine t minus 2 sine t dt. Okay. So I think the rest of the parts is not that complicated, but I think maybe. So I was intending to give square here. So let's put it square. If I don't have square, I think it's getting more complicated. So anyway, what is it? So I have 4 2's, so I can get 16 out. And we have sine t cosine cube t plus, and we have sine cube t cosine t. So I changed my xy on the second coordinate of vector field into x square y, so that I can make it simpler. So I think it's a typo here. So anyway, in that case, what I get here is canceling out something inside. It's sine t cosine t dt, and you can do the rest of the calculation easily. I think it's 0, right? I think it becomes 0. Okay. So, well, let's think about the curve. So it's not a, oh no, it's a 2 pi. Sorry, it's a pi, right? So maybe it's not 0, but you have to compute. So I think it's 0 anyway. Anyway, so think about the curve. So basically, it follows the curve around the circle whose center is origin and the boundary. The radius is 2, but you are where starting at 0, that means you're starting at here, and you're ending at pi, so you get to here, and then you're actually following what? Negative side, minus x part, so you get following here, right? So it's a half circle, so you're moving along the half circle and try to compute the work done by this force field. Okay? So that's how you compute the line integral of vector field. Well, there are many examples, but let me give you another way of computing the line integral on the vector field. So these are two ways you can actually compute. So here we don't have ds. First, the line integral of a vector field is denoted by ds. Here, f and s are considered as a vector. So here, f is of course vector, but ds on the line integral of function, we had ds just implements that implies the infinitesimal distance. But in the line integral of vector field, it's not infinitesimal distance; it's infinitesimal displacement. It represents the velocity. It represents how much it moved inside of this two-dimensional space or three-dimensional space. So it's a vector. It's considered as vectors. That's why we have inner product symbol inside of a line integral. But think about this way. I can rewrite this ds into three components. The component for x direction, y direction, and z direction. So since I have c prime given as xt, yt, and zt, and I can take the differential to get the velocity, t and z prime t. So here, usually what happens is I replace that ds into c prime dt, right? So what is the c prime dt? This is same as x prime dt, y prime dt, and z prime dt. So now think about meaning of x prime, y prime, z prime times dt. So when you move along x-axis with the speed of x prime, it's actually not speed, it's a velocity, but it's a plus minus speed, times dt, it gives you the amount of change in the x direction, in the x-axis. So you can replace this by dx. You can think of this as dx over dt times dt equals to dx2, because x is simply a function in terms of x, the single variable function. And same for this part, it's dy and dz. So I can rewrite this as f vector field inner product with dx, dy, and dz. Well, I'm just manipulating with the symbol, but only because it makes the same result, and I'm not giving you the detailed meaning of this, but just giving you the way it could be calculated simply. So when I rewrite the symbol, like a symbol of line integral in this way, what happens is, let's say my function f is the vector field of PQR. And now I'm taking the inner product with dx, dy, dz. Sorry for not having a space here. So what happens, well, all the way back here, is that I'm taking integration of p. So p is multiplied with dx, dx plus q dy and r dz along the curve C. So, well, okay, that's what exactly I wrote here. And what's good about this is that I can actually split these three integrand into separate integral. So first I can integrate over c of p dx and c over q dy and c over r dz. And then you can compute all three line integral independently and then add them up to get the entire line integration. So you can actually do this in the line integral of vector field. So You see, I'm trying to give you the connection between ds in the line integral of a function to the ds into the line integration of a vector field. You have to think about the meaning of what ds gives. So in the previous example, like in the line segment, we had to interpret our ds into dx, dy, dz. In here, your ds, the vector, the small increment to some direction, is actually composed of dx and dy and dz. So think about this one. So simple computations, but it could be done by simple calculation. So again, this is a symbolic notation, that meaning that we want to integrate my this specific vector field along this curve shown on the right. But you can write that out in terms of dx and dy like this. Okay? Now, as I said, this can be done by treating this integrand separately. So I want to integrate minus y, xy, dy squared dx first, and then add with x over x squared plus y squared dy. So let's do the first one first. So in the first integration, what I'm doing here is I'm only changing the x direction. So I only want to consider how much I changed in the x direction, right? But however, my integrand, my function, has a value of y. But luckily, when I moving along these directions, L is 2 and L4, I don't have any change on y. So I can consider y as a constant along this y2 and y4. How about y1 and y3? When I move along y1 and y3, I don't have change on x direction. So my dx, which computes the distance I travel along the x-axis, are 0 when I move along L1 and L3. So even though I have to integrate over entire closed circuit here, I can only take the line integral along L2 and L4 to get the real value, because the line integration over L2, L4 are 0 anyway. So this becomes line integral over L2 plus L4. And how about this one? How can you write the line integral into two line integral? What are the paths that gives you non-zero, that could give you possibly non-zero value? Along L what? Yes, L1 and 3, because that's the only way, only part that changes the y, and the other part has no change in y. So L1 and L3. So let's try to get L2 line integration. I'm taking del minus y as squared dx, right? So in L2, I'm changing my x from 1 to 2, right? That's my parameterization, because I need to consider the orientation of the parameterization. So x is changing from 1 to 2. And what's my y value? Minus 1. So it's 1 over x squared plus 1 dx. And we know the integral, antiderivative of 1 over x squared plus 1. It's arctangent. And I'm changing, taking from 1 to 2. So it's arc2 minus arctan 1. Okay. And how about L4? When you're integrating L4, what's your domain of integration? Well, it's the same thing, but you have to be careful about the orientation. In L2, you're changing your x from 1 to 2, but in L4, you're changing x from 2 to 1. Okay? So it's not 1 to 2, it's 2 to 1. So your lower limit is 2, and upper limit is 1. And that makes perfect sense, because you simply plug into the Riemann sum. It's just changing your partition from 2 to 1, not 1 to 2. But also you can remember the integration technique, that if you change the sign, limit of your definite integral, you change the sign. So what's the y in this case? Y is stayed in 1, right? So 1 over x squared plus 1 dx. So same here we have arctangent x from 2 to 1, which is cancelled with this one, right? It's 0 here. Is it? Yeah, I think so. Yeah. Yeah, it's 0. And you can do the same thing for L1 and L3. So I'll let you do the L1 and L3 part. So try to think about, try to compute the second line integral L1, along L1 and L3. If you need more paper, you can pick up some paper. I think there's a typo. I thought it was weird too. Okay, so this is not 0. So this one, we have minus y, right? So when you go through L4, it's 2 to 1 that x changes, but y is 1, so you get minus 1, right? Because you have a minus y. Y is 1 along this L4. So along the L4, you have y stays 1, so you get minus 1 over x squared plus 1. So that's your integrand. Okay, so you actually get the same thing. You're not canceling out with this one, so you don't get the minus of this. So you get something different. So use the same idea for getting the line integral over L1 and L3. okay, you can compute L2 and 4. Well, I just gave you the idea. I didn't write neatly, but you can compute L2, L4 too. So when you compute all the line integral on every pieces of this line, you get a canceling out every terms. You get entirely 0. Okay, so 0 is the final answer of this line integral. So you can see what happens, how you can compute the line integral easily by just symbolically breaks your line integral into smaller pieces. But you can actually done it in a non-straight line path. So think about our situation that our curve is a circular curve centered at 1, 1 with the radius 1. So I want to compute the line integral of this, so which means that my vector field is x squared y squared. And as I said, you can symbolically write the line integral this way, but also interpret this symbolic notation as if you're taking the line integral along x or y. But now we don't have a straight line. So what should we do? So first think about the line integral dx first. X squared, and here y squared. So what you're actually doing here, so it's not the definite integral, although it only have x variable in the integrand. You have to think of this as a two variable function that the y part is missing because of zero coefficient, whatever. And same thing for here. We're not taking a definite integral on the single variable function. We are taking a line integration of vector field. It's simply saying that I only consider the increment in x direction of the vector field whose y coordinate is 0. And also in here, I'm considering the y coordinate, x coordinate of the vector field is 0. So that's what I mean by these two line integral. So when you take the line integral of the first type, how I look at the curve is separating into two pieces, the top and bottom, because I have to do it because if I think of this entire one path, each coordinate of x gives me 2 points. So I don't know which point should I look, right? So I need to have one-to-one mapping of x coordinate to point on the curve. So that's why I have to split it into two. And as I said, in the problem, I want to take the orientation counterclockwise. So the top part goes from right to left and bottom part goes from left to right. So let's write the first line integral. So first line integral x squared dx is now separated into the line integration over C1 and C2. And think about the line integration over C1. And C1 start from, now we're looking only at the x coordinate, right to the left. So on the right it's 2, and on the left it's 1. So it's 2 to 1. And x squared, now x is already the variable that we are parameterizing our curve. So x is x and dx. That's all. Okay? It's simple as that. Okay, so we don't have y, so therefore we don't have to consider the change in y. So if there was the y variable inside this integral, then I need to plug that y as square root of 1 minus whatever, something. I mean, maybe 1 plus square root of 1 minus x squared. But we don't have y, so that's what this is what I need to compute. X cubed 2, 1. But I'm not saying that, so up to this moment, it's now same as the definite integral of a single variable function. But here, it's not the definite integral of single variable function because we could have y. So how about C2? So I'm taking integral from 1 to 2 of x squared dx, and same thing as x squared, 1 to 2. Well, actually, that cancels out, right? So how about on this part? So we get the, wait, oh, I pasted the same picture here, right? So it shouldn't be this. Right, so on the second part, so when I try to compute the y squared dy integration, I only want to see the changes in y, right? So in that case, I want to see where my point is for each coordinate of y. So therefore, I need to parameterize my circle into two pieces like this one, C1 and C2, right? So on the C1, when I have y value, then I can map exactly one point on the curve. So that's that point. And on C2, I can map this point. Okay? So this integration separates into C1 to C2. And on C1 part, it's from 2 to 0. 2 to 0. Oh, sorry, it's not 1. It's actually 0, sorry. 0. And on the C2 part is 0 to 2. So it cancels out again, because what I'm doing here is just integrating y squared. I want to see the changes in y, but when I change the y coordinate, the x coordinate, of course, it changes too, but in the integrand, there is no x. So I only need to see the y. So y is already the variable that I'm parameterizing the C2 and C1. So it simply becomes a single variable integration. So it's 0. But if you try to, well, you can try the same way we define the line integral by parameterizing entire circle into cosine and sine and then plug that into here. But it makes the integral just complicated. But if you use this notation, it makes actually simple. That's what I try to emphasize. You can have this integration symbol to make your computation simple. So there's one more part that I want to emphasize. So it's a short one, so I will just shortly introduce. So when you have a function when you have a vector field and has a real valued function that has this relationship that your vector field is given by the gradient vector field of your function, then this function is called the potential function of a vector field. So it's just the potential energy of a force field. So this is a theorem about the gradient vector field. If your vector field has a potential function, then whatever the line integral that you have of that vector field is, it only given by the difference between the values of potential function. So in some sense, it's the same in the physics theory. If you have a conservative vector field, we'll kind of talk about that kind of notation later. Then when you take the line integral of a vector field, which means that you compute the work done on the object to move one point to another, then it's turned into an energy that this object has been received, and the amount of energy that the object received is changing the potential energy of one point to another point. So that is the difference we have in here, FB minus FA. So in this case, let's think about this one. Let's say we have a two-variable function given by arctangent of y over x. So it actually measures the angle of a point. So we are not looking at entire two-dimensional plane. We're only looking at the half of it. So it's on the x positive side. So whenever you have x comma y, you have an angle that measures from the positive x-axis, and this function fx comma y has value equals to that angle theta here. So I want to find out the integral over the curve. Over the curve of the gradient vector of this function. So as I said, because of the theorem, it only given by the difference between the value of function from the start to the end. So what's the curve? it's a straight line following this x equals to 1 line. So we are looking at x equals to 1, and we're starting from minus 1 and at plus 1 according to the y. So this is my curve C. So you could try compute the line integration by computing what the vector field is, because it's given by the gradient. And also you can have you already have a parameterization, plug that parameterization to get the line integral. But think about the theorem. I can just simply compute this by the difference between the value of potential function at the end and the start. So what is the value of potential function at 1, 1? It's the angle of 1, 1 on this plane, pi over 4, right? And what's the angle at the 1, minus 1? It's minus pi over 4. So it's pi over 2. So you don't need to compute the line integral at all, because we already have known that this function has, this vector field has a potential function. So in some sense, this potential function given from the arctangent is the vector field that measures the difference between one point to another of the angle that that actually measures, the line integral actually measures the angle difference. So it's called the angular vector field in some literature. So anyway, so that's what I wanted to say. And on the next time we're going to talk about, so far we talked about the line integral, and the next time we're going to talk about the surface integral. So it's similar idea, but we need a little bit more geometric concept, but not that different from the concept of the surface that we discussed last time to define the area, the concept of area of a surface. So if you have a question, let me know, or we'll see you on Wednesday.